Okay, so now let's go into class number 3 after we just reviewed the other one. And in class number 3, this is our agenda. Let me make it a little bit bigger. We're going to start looking at control statements, and control statements are basically how do we allow the program to move through the flow of things. A situation where we have an if else. This, by the way, this guy right here is a flow diagram, and this is pseudocode. So these are nomenclature that it's actually used in to like represent some big logic or something. You know, like if you're trying to do a design document for a certain architecture or something, you might not have to like do the entire diagram or the entire algorithm this way. But if you have a rough idea of an algorithm, you can present it this way without having to write code. And for example, what would be a good idea of an algorithm that could be represented with that? Well, let's assume that we have a web page and the user logs in, and there is a login page, and if we can say this type of diamond, it is, oh man, let me see if I can make it. Let's just put auth. If it is authenticated, if it is not authenticated, then it'll take you to unauthorized. And if it is, then it will take you to the home page. You know, this is just a way of representing a typical flow where the decision is expressed by that diamond. So there's also ways of representing something similar with what is known as pseudocode. Pseudocode is just basically, without applying any syntax, if a human read this, would that other person understand it? And in this particular case, you know, like the if and else, we're saying, okay, if A, then B, otherwise, then C. And, you know, this is very simple for those of you that have done coding previously. But for those of you that haven't, let me just make sure that this is fully clear. Let's get some numbers, please. Okay, perfect. Yeah, this is simple enough. And the syntax in Java is that we use the keyword if, and then we put the condition between parentheses. That condition has to be a Boolean. And then either a block or a statement goes after that. And then the other keyword would be an else for other conditions. So let's go into our trusty IntelliJ. We're gonna right click, create a new Java class. We're gonna call it class 3. And then we're gonna add a main method. And then we're gonna put, actually, I'm gonna copy some of this code from here, what we had created. And if yes or no, We can say something like system.out was print yes, else no. And this is just essentially a random way of presenting an if. You see that that yes or no returns a Boolean, which goes into the yes or no function. And essentially, you know, every time that we run it, it's gonna return either yes or no in a random way. So let me does anybody need some time to copy these? Yeah, okay. Let me give you then a couple minutes. Put it here. And let me give you 3 minutes so you guys start copying this thing. Okay, then. Let's move on then. So now we understand the if else. What would happen if we change this to int and we generated it if it was between 0 and 3 and we returned, let's even put like 10. Well, no, let's do 3. So that way we have 0, 1, and 2. So I'm gonna comment these all out for now. And I'm gonna put system.out.println, yes or no. And right now you can see if I run this guy, it's 1, -1, and 0. What we're gonna do is that we're gonna convert it into like just 0, 1, or 3, because otherwise it is, actually there's gotta be a way to like make it positive. Well, we're forcing it to just be 0, 1, or 2. 1, 1, 0. Oh, let me master that shortcut because running it is, oh, there you go. We'll run it again, 0, 2. So this method is returning anything between 0 and 3. Okay, let's uncomment this. We know that because it's returning 0, 1, or 3, let's just store it as int value equals 0, 1, or 3. So if value equals 0, then we can put, you know, 0. If we got, and notice the else if, that it's a nested thing, I can put like value equals 1, 1, else two. You see, I am translating right now by hand whatever number is coming in. But I am saying, okay, if the value is 0, then print 0. If the value is 1, then let's print 1. If otherwise, for everything else, that's 2. So, and maybe just to like make it a little bit more evident, I'm going to add something like this. So I am going to print the number and whatever value that I'm getting. So 2 is the value that was generated randomly, that it's 2. It's, you know, continuing to print that, 0, 0. That means that, if it's making the match of that value equals 0, then it's going to go through this path. If it is mapping the 1, it's going to go that, and everything else is 0. Let's prove that everything else goes into this bucket. So if I make this 10, only 0 and 1 are going to go into these two values, but everything else that is not 0 or 1 is going to go into this one. Everybody following me? Let me just make sure that everybody's following me. Just type yes, or just type Y or N if you are following me. Okay. Okay. So if I am running this over and over and over, you're going to see that eventually, because I'm mapping 10 values, I'm going to get something like this, 2 and 8, because I ended up capturing everything that was not 0 or 1 in here, in that same one. Okay. Let's get some numbers, everyone. Just about if else. If else, else if. Okay, perfect. Fantastic. Okay, so now that we understand that, and we understand that if, else, if, and else, we can go into another kind of if, which is the switch and case. And for this one, I wanna make a difference, because some people, and actually I've seen some people actually utilize this in a very bizarre way. But let me just make something a little bit clear. Let me just switch to sitting down, because I needed a little bit of a break of sitting down, but now I need it back in here. So, so far, we did some mapping that we have a scale for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So basically, our code that we just wrote is grabbing any of these numbers, right? And our conditions, and let me just grab, our conditions are explicitly set for, well, let me put it this way. This value and this value, meaning this is a else if, this is a if, and then this is the else. This is a visual representation of what we just did. So, as you can notice, as long as we are doing something Boolean as a condition, there's nothing in the if else statement from making us do something like this, where our if goes and uses these guys, our else if uses these guys. And then this is the else. You can see that if we did something like this, and actually let's even translate it to that, because I want to drive a point once we switch to the switch case. So we can put something like, if value is less than 3, right? Then we're going to print 0 and then the value. If that value is less than 5, then it's covering, I mean, less than 6, sorry. It's covering the blue part. And then else is going to cover the red part. So if we did, again, our running exercise, we're going to see that 0 is 2 because it's covering with the red. Let's put it red. Let's change this to blue. And let's put this one to yellow. So it's a clear representation of what we have in here, right? Mapping against the colors. So we have blue, because it's in the area. Blue is between 3 and 5, so it works. We have yellow because it's 7, and so on. So these cases might not, this might seem like too much of a duh for somebody that has already some programming experience, but this is why I've wanted to show you this way. You can, I want to just highlight the fact that an if basically is allowing us for a range of values. And if these were actually floating point numbers, anything that is on the if would be, from 0 all the way to 2.9999999, all the way to infinity. So you can see that it's somehow a big, it's covering a range of values. In the case of the if, it's same thing. It's covering a big, somehow a range of values, and in the yellow range of values. Okay, the fact that it can cover a range of values is the biggest distinction for a switch. A switch is a similar comparison. And let's go in here in the slides. Where do I have the slides? A switch is a similar comparison to an if, but each item on the case is a discrete value that it's comparing against. So you can see here, there is no if it is less than. It is actually just looking for a bunch of equals. So while on the if, again, let me just repeat that. While on the if, we can use any of the regular Boolean operators for an if, which opens up, greater than, lesser than, et cetera, et cetera. On a case, basically the only comparison we're doing is equals. That's basically the only comparison that we're allowed to do in a case. So for that reason, a case, I personally would recommend, let me just erase this. For that reason, I would personally recommend that a case is used in a set of known number of items. The only exception for when in case is not using an equals is for the default case, meaning essentially the else. So with a switch slash case statement, we cannot perform an operation like this. However, we can perform an operation, and I'm going to put it with dots, like this. which is the original case that we had. Does this visual representation help, I guess, make it a little bit clearer the difference between the if and the else? Again, because we only have the capability of doing equals, we can only have for each different case item a single value, not a range of values. That's the biggest difference between a switch case and an if. Let's get some numbers so far. Let me just make sure that we're good with that distinction.
Hey Juan.
Yes.
I think you deleted the code, but you wrote something before you wrote the switch case.
Mm-hmm. I haven't switched the case. This is that.
Yeah. So what if you? Because I ran into this or I guess when I'm doing the homework, I guess I noticed like if you switch say you switch the else and the else if statement. Oh, I'm sorry. So say if you switch the else if and the if statement, because it seems like it can satisfy both. Like if you do 2, if the value is like 2, it can satisfy that one and also the other one.
Oh, I see. Yeah. So what you're saying, let me put it in a little bit above. What you're saying is if we start evaluating if value is greater than 6, basically that condition, lesser than 6, that condition, and that's where logic actually matters. Basically, your condition would do this. And because, and then if we swapped it, let me switch colors. Your if value is less than 6, it would be value lesser than 6. Then you have your next statement would be value lesser than 3. And because instruction already covered the first one, it wouldn't be executed.
Like you would never see blue, or you
would never see blue, right? And then your else would be this.
Yeah.
So it's a totally different approach than what we had, and even if, let me just put them side by side by the current order of operations, which is.
I guess my question is like, do you have to just keep it in the right order? Is there like a more secure way to like, no matter what order you put it in,
it depends on what you want to do. Actually, no, this is actually wrong. I would move it like this just to make it map. But the order of between this, and if we swap them around the value greater than 6, in here we have value lesser than 3, and we have this one as value lesser than 6. So this is it just depends exactly on what you want to do.
Wouldn't the more secure thing to do to set up the the ampersand operator and create an inequality with 2 sides?
You could, but it's more verbose, and then you're going to get certain warnings from the compiler. The compiler is going to try to optimize that. So the compiler is going to be like, oh, this expression is never going to be hit.
So does it just prefer it to be in that order then? Like that's fine.
Yeah, I would pay special attention on the way that you are, I wouldn't always say like, oh, start in ascending order, because your algorithm actually might be in descending order. Here's an example. Actually, it's one of the things that we have to do on this week's assignments. We have to reverse a string. So if you're reversing a string, obviously you're starting with the biggest item, and then walking your way all the way down to 0. So you start from, the end to the beginning. So in that situation, obviously you want to evaluate the bigger numbers first and then the smaller numbers later.
But
I guess the better recommendation from me would be make sure that the values that you are mapping, or that you are the conditions, are well thought of. That's it. If you think about them well enough, then you won't have any problems.
okay.
So then going back to the switch case, because this is something, so everybody has this, everybody's okay with this. I can start modifying it. So we know that a case like this we can't do in switch, but we could do the opposite, the one that it's with the dots. So we can do switch, and then we say we switch value. We are going to switch the variable, and then we're going to apply each individual case. So we're going to say case 0. Then we're going to say red value. And I'm skipping something on purpose. For those of you that are blue, and then default yellow. So we have yellow is essentially, these two now, it's correct. We have it here. And if we run it again, yellow 4, yellow 9, but I wanted to, hopefully we'll get to, okay. So we got the case of 1 and then it printed yellow. Switch also allows us to cascade alternatives. That depends if we are going to, like, if we use the keyword break, all these guys, the moment that it finds that condition, if it finds the keyword break, it stops the execution of the switch. If it doesn't have that break, it continues all the cases until it finishes, or until it finds a break. One of the two that happens, that could be happening there. So now that I introduced those two breaks, we should, whenever we find a blue, it should stop and just blue. It should not cascade to the next yellow. Does this make sense? Let me make sure that everybody's understanding this part. Well, we'll do numbers after we actually visually see it. So let's right click. See, now we got blue, and it stopped at that blue.
Sorry, Juan, could you explain like why we got 1 for yellow? Or yeah. Also, like we got blue 1 and then yellow 1.
Yeah, the reason is because there wasn't a break statement. So in a switch, let me write it over here in the dashboard, in the whiteboard. In a switch, if you have case 1, case 2, and default, if there is no break, it will start wherever it found. Let's assume that for the same set, it started as blue, printed the blue, and because there was no break statement, it went to the next one. It continues cascading through all the elements until it finds that break statement. It's a feature, not a bug. And I'll explain what we can do that actually is interesting with that behavior. If we introduced the default keyword, then it stays within its own realm. So right now, if I put again that break, it just stayed within blue.
So default is actually like just it can be 0 through 10.
0 in this case is 0 through 10. Yes, because we have not built a specific case for all of these. But that's why I'm saying, like, if you have a specific set of items that doesn't require that value of range, you know, like in an if, we can say, like, if the value is lesser than 2, then, you know, do red. If it's less than 5, then do blue. In here, we only have one very specific case. There's only case 0, which is that red. Case 1, which is blue, and yellow, which is the rest.
So if you didn't have breaks, if you got a 1 or a 0, you'd always have 2 items, right?
If you have 1 or 0, yes, yeah,
Okay.
yeah. Okay, so the break is really important to, like, exit. Break essentially means let's get out. Let's get out of here. But what are the situations where we actually don't want, like, we could use that type of cascading? I'm going to show you. Let's see, there's got to be a. I think, you know what? What is Circle CI? If we go into pricing, you can see something like this: free, performance, and scale, where you have model 1, and then for model 2, well, you have free, and then you have tiered performance and scale. If we model this thing with a switch where, you know, depending on the value that the user chooses, because we're not including that break, you get, when, let's assume that you choose the scale, what's it called, package. So you land here, and then after that scale, you get everything, you get the features of scale, but you get everything that performance has, plus everything that free has. If you ended up landing at performance, then you get everything that performance has, plus everything that the free tier has. So you can see, like, an actual real life example of using that cascading, how we could write something quite elegant without repeating code. Now, there are other limitations to the switch statement. Other than the cascading and stuff, that it's an actual feature, not a bug. A switch statement, oh, let me switch back to black. A switch statement supports either numbers, characters, and it only supports one type of object, a string. So let's let me int, string. We have scale, performance, and free. We have these arrays, and if we did that value, which I'm switching this code to just What did I do? Okay. I'm gonna comment this for now, for a second. You can see that now the plan function is returning randomly one of these three plans. Free, scale, it's randomly returning one of those three plans. So if we did this using, using the similar thing where we are putting scale at the top, the one that is the most inclusive, and we remove and then the default is you can see that the features, scale features, let's just add features. The things that we're going to include, and this is oversimplifying it, but our plan is free, you only get the free features. If we run it again, plan is performance, you get the performance features and the free features. You saw how it cascaded. It landed here and it went from and performance and then free. Let me rerun it again to try to get it to run to scale. Here is scale. You get the scale features, you get the performance features, and you get the free features. So that's why I wanted to show, like everything there is about the switch. It would be lazy for me to just tell you, oh, it's similar to the if. But there are reasons why to use a switch, and there are reasons why to use an if. There's no such thing as primitive strings. A string is, so yes, plans just will return one of those three items. Now, a string is always an object. That's why I'm saying a string is not a primitive string. A string is an object. That's it. Even though that Java has certain exceptions for how to create it, a string is always going to be an object. The plan function is just returning one of those three randomly. And depending on what we got, the idea of putting that randomly here is so that we can explore how the switch behaves and how the if was behaving. Does that make it a little bit clearer, George?
Yeah, I got it. I didn't see plan actually. I just was confused. No, I saw it. All good.
Yeah, let me make it a little bit bigger. Okay. So now that we're that I explained everything there is to be about switch, let's get some numbers about switch and if. Okay, perfect. So seems like everybody's understanding this. It's very basic, but I figured that these type of visuals actually do help to understand those differences because they're important. Okay. Oh, do you guys need time to copy that example? Yeah, let's give 3 minutes or 5 minutes, because it's a little bit more text. So let me just give you guys time to copy those. And let's make sure that you guys have what you need. Okay. Technically, I could have just, be like, okay, let's move on and the class is recorded, and next time we're gonna, or I'll let you guys do it at your pace. However, one of the things that I do, a lot of the elements of the class actually have a reason for a reason. So if I put those timers to like copy the code and stuff like that, it's also to give you the chance of trying out the code and then raising your hand if something didn't work. That way I can help you troubleshoot it. Second, it is pretty like a lot of the good intentions of like I can go back and fixing it or do the exercises later. Truth is that in a busy world like we are, finding the time to go back and like really do all those exercises might not really ever happen given everybody's time constraints. So I would recommend you guys to really copy those exercises. Then that way, as the class progresses, you can start getting more and more familiar with the code. Also, I'm not going to go immediately right now into the break. I just want to, because we started a little bit. I mean, it extended 5 minutes a little bit the class. I know we're going to make it back once we go into the arrays portion of things, but I just want to explain one of the loops, or one of the couple of loops, and then we'll go into that. So again, loops. Right now, I'm essentially putting it in a way that you can remember them, like the rinse, wash, repeat that you find in the shampoo bottles all the time. It always says rinse, wash, repeat, or wash, rinse, repeat. Yes, it's backwards. Anyway, the idea here is that if you have a condition, if it is true, then something happens in that loop, and then it goes back into evaluating that condition. And that will continue repeating until that condition is false, and will continue the execution of the program. I have a simple loop here, which is using the while keyword. While A is true, then do B, then end while, which is this loop, and then end the while. Whiles are represented in Java using the while keyword. And while is essentially, while this condition is true, then execute this. And then when it is not, then exit that loop. So this seems pretty straightforward. Again, if I go and let me just put this as a, I'm going to delete this for now. And we're going to do a counter from 0 to 10 with different methods. So int x equals 0. And we can do while x less than 10, x plus plus, and then we're going to print at the very end of the loop, we're going to print the value of x. So this counter is, it just happened, you know, it repeated that counting of things 10 times. Let's actually put it here and debug it. You can see that I'm going to continue playing the value currently is 0. I'm going to continue playing this guy. It's going to stop at the next iteration, which is now 1, next iteration 2, and so on, 3, 4, 5, 6. And I'm going to do it right now just with each step. It's going to continue. You can see that it's evaluating all the way until it gets to 10. And then once it gets to 10, it stops and leaves the actual loop. Incredibly simple. So simple that it's a little bit ridiculous. There's another type. There are 2 more types of loops that I'm going to cover. The next one, it is known as do while. Do while is really useful when you want something to be done at least one time. when would that be actually useful? Well, if there, here's an example of something that you guys know how to program, but haven't really thought about. An array of unsorted numbers. If we wanted to see if the array is sorted, at the very least, we got to check all the elements to see if they are in order. Basically, as we are reading through the array, we say, okay, is this the smallest number that I have found? Well, currently 1. Yes, it's my smallest number. Is this one smaller than 1? Nope, it is not smaller than 1. Is this one smaller than 1? No, it is not small. You know, like, so it's eventually you're going like number by number to review if the array is in order. So even if we had 1, 2, 3, 4, 5, 6, 7, something like that, and we went, okay, is the smallest number 1? You know, like, I'm going to erase this one for now. Our smallest number is 1. Hang on. Our smallest right now is 1. Okay. Is then, or, you know, let's assume that the current greatest number, I would say the current greatest number is 2 greater than 1. Yes, so you can go after. Okay. Is 3 greater than 2? Yes. Is 4 greater than 3? Yes. Is 5 greater than 4? Yes. So, you know, as we're progressing, we are like putting 4 and then 5, 6, and 7. So we're checking the array. All of these is just to say that we would be checking all of the elements of the array at least once before saying, yes, it is in order. And we're going to go through the algorithm of sorting an array in a little bit. Do we go through that today? I think so. Well, so basically, a do while allows us to say, do check the array. This would be like a way of making a really bad algorithm because it's not efficient, but it works. Basically, if, or no, do check array if, actually, no, sorry, I'm writing it wrong. The do starts like this. Do this is just a hyper simplified way of doing a do, just checking the algorithm. Meaning, do we need to swap numbers to make the array in order? So in this particular case, the first pass of finding the array, these two numbers, we would need to swap them because we would go pair by pair we would go these two numbers, then these two numbers, then these two numbers, then these two numbers, then these two numbers. And if we did that comparison, going 1 versus 4, do we need to swap? Let's actually go through that. 1 versus 4, do we need to swap? No. Okay. 4 versus 8, do we need to swap to put them in order? No. 8 and 3, do we need to swap? Yes. I saw Josh nodding. So yes. So here we would swap 3 and 8. We would swap these two, 3 and 8, and then this is now set to true, whatever these function the check would do. And 8 and 2, do we need to swap? Then
Yeah.
yes, we would need to swap these two because 8 is bigger. So then we would do this. We know that we have swapped once, at the very least, if we had swapped. And then these two, do we need to swap?
Yeah.
Okay. So do we need to swap? Then we have swapped 3 times in this particular case. And because we have swapped, that's the value. While we have swapped, while we have swapped, then we do this again. So then in this particular case, 1 versus 4, do we need to swap?
No.
Okay. Then 4 and 3, do we need to swap?
Yeah.
Okay. So then then we need to flip these two guys. Now the flag, what was the values of 4 and 3? 3 and 4. And this flag is now in true. 4 and 2, do we need to swap?
Yep.
Okay. 2 and 4. 4 and 5, do we need to swap?
No.
And 5 and 8, do we need to swap? Okay, so we return this flag, so then we do it again, which means we start with a flag again in false. I would have to put this guy here, actually. Let me fix this, my algorithm. Do swap equals false. And that way we initialize it to false. Then, okay, 1 and 3, do we need to swap?
No.
Okay. 3 and 2, do we need to swap?
Yeah.
Okay. Yes, we do need to swap. So win and 3 and 4, do we need to swap? 4 and 5, do we need to swap? Oh, and because we just did swap, we changed this flag to true. 5 and 8, do we need to swap? No. Okay, we return this and then we do it one last time, which is essentially this thing. Okay, so we start again with false. 1 and 2, do we need to swap? No. 2 and 3, do we need to swap? No. 3 and 4, do we need to swap? 4 and 5, do we need to swap? No. 5 and 8, do we need to swap? So then we return false. This completes that algorithm. Again, if we just got this new array, just following that same algorithm, if we just got this guy, at the very least, we gotta do that pass one time, making sure that all the elements are in the array. Do we need to swap? No. 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 Therefore, we know that the algorithm is correct. Again, do while forces things to happen at least once. Okay, so then let's give me some numbers about while and do while. Okay, perfect. So then let's take our break. I'll see you guys at 8:30, so you can get a little bit of a downtime. Our 20-minute break, and then we'll continue at 8:30. Okay. All right. See you in a little bit. Okay. I hope everybody's back. We still have a big agenda in front of us, so we want to make sure that we catch up. So the next item, as far as loops goes, there's one that is a little bit different. This one has a built-in counter. Basically, what this one is telling us is that if we have there's an initial condition, a condition that sets a variable that only lives in that scope. While that condition is true, then that increment will happen. And the easiest way to express it, this is a typical for that you might see everywhere else, where you have, let's do the same counter, or int x equals 0, x less than 10, x plus plus. And this guy has a built-in counter here. You can see that that is basically in the scope, but we can print what the value is of x. And it's very straightforward. It sets an initial condition. While that condition is what it's still going on, it will increase the counter, and in that body it prints that. So you can see that here we had the 10 items that it counted. That one is extremely straightforward, and you know, there's nothing really special about that. Now there is one extra one, but I'm gonna come back to it, which is this for each and the iterator. We're gonna come back to this guy after I talk about arrays. I've been jumping ahead and talking a little bit about arrays before we even define them, but I'll come back to this guy because it's gonna take no time. So there are a couple of other concepts or a couple of other keywords that I wanna highlight, which is break and continue. And for that to happen, I am going to go to Google Maps. And let's assume that there's this area here which is very much like a grid that I actually like to use as an example. Let's assume that we have a pizzeria, right? And our pizzeria, let me just take a screen grab and then go here. Okay, the pizza place is right here. Is there a way that I can actually, yeah, I'm gonna make this a little bit more opaque like that. And here, where the blue is, can you guys see it okay? All right, so in that pizza, we have a pizza place and we have some orders. This, you know, our delivery radius is this guy here. Let me make it a little bit bigger. But yeah, our delivery radius is in that area. So let me go for thicker. There you go. We're going to end up delivering pizzas here, here, and here. And if you see anywhere like, you know, pizza delivery, some places in the world actually they deliver pizzas like this, where there's a dude in a motorcycle and they put the pizzas in the back. There's a limited capacity, and that's part of why I'm showing that problem. So we have one of these guys that it's delivering pizzas like this, or, you know, something like this, where there's a small capacity in the back, where basically we have given the delivery guy two conditions. One, in order for you to go to the pizza place, because of street closures, we have, let me make it a little bit bigger. a little bit thicker. Okay, so directions go in this way, this way. The street, the way that streets are going, it's a single direction. Let's put one here. And the street directions go pretty much like this. This is for street closures. That is the order that we have to deliver, like, you know, the directions. Let's assume that this is not, you know, what is this Wilshire Boulevard, that it has two sides going on. Let's assume that there's only one direction. So our pizza guy is very respectful, and he is going to start at the pizzeria and going to start navigating the pizza place or the addresses basically in this order that I'm going to put here. So it's going to start by doing this, then it's going to go here, then it's going to go here. Actually, let me change the direction of this one. I want this guy. Oh, what am I doing? This is the direction. So basically, the pizza guy is gonna go in this route to continue delivering the pizzas. Basically, that's the route of the pizzas. So far, so good, right? Okay. Because the pizza, the motorcycle only has the capacity for one pizza. The moment that the delivery guy delivers one of the pizzas, it is advisable that he does not continue the route. In other words, let me find another color. Let's find purple. We don't want the pizza guy, for efficiency, because otherwise he would take all day, to do this throughout the entire, deliver the pizza, continue. What we are hoping that the pizza delivery guy would do is that he delivers the pizza and he goes back here and then back again to the pizzeria. Then the next pizza that he delivers, he is going to do this, you know, because he is only following that route. He would then go here and then would come back directly back into the pizza place, and so on. Like, essentially, as soon as you're done with your task, come back, grab the next pizza, and deliver it to the next client. So far, so good. Everybody's following? Yeah? Okay. So when we stop right after we deliver the pizza, there is one keyword that emulates that in a loop. And the keyword is continue. Essentially, as soon as you deliver the pizza, go back to base and continue with the next one. That is continue. Let's assume that our pizza guy delivered this first, then this second, and this third. And then the third pizza was delivered at 6 p.m. Meaning he is done for the day. If the pizza guy is done for the day, should he go back to the pizza place to complete his shift, or should he go back home? I would say that, you know, because he knows that's the last thing on the pizza, and let's assume that there's no logistics of returning the motorcycle or anything, he can go home after that. He can exit that loop of figuring out what is the next pizza and going in and getting all that. So that behavior is known as break. But you see how in both situations, the continue and break, there is an efficiency item. In both situations, is do not perform unwanted work or unnecessary work. Essentially, we would be cutting, going back and waiting for the next pizza or waiting for the next item. That is with break. That completely terminates the loop. Continue, it goes back to the condition and then continues executing it without executing the rest of the unnecessary work. Now, let me make sure that this analogy connected with you. If not, then I have to find out a different way to explain. Let's give me some numbers about these two keywords. Okay, so Josh and Brandon, let's review what's missing.
Yes. Would you be able to? I know you're probably going to go through a coding example, but I think that would be better for me.
Okay.
For a little bit for me. I don't know.
Josh, same for you?
Yep.
Okay. So let's actually actually let's even do it like let's do 100, and let's assume we want, because we delivered 30 pizzas is usually the pizzas per shift, and we have 100 pizzas to do. So let's say that we're paying for 30 pizzas, even though that there are 100 pizzas in the oven. And well, or in the queue for the oven, we don't have an oven that big, but we have 100 pizzas that we usually make, and per shift, we're only going to do 30. So if let's say if X is greater than 30, which is the number of pizzas that the pizza delivery is going to do, we're going to do break. So I'm going to just print X. And you're going to see that even though the counter goes all the way to 100, I'm exiting the loop. I'm forcing an exit of the loop at 30. You see, it's what happens if I comment out the break. It goes all the way to 100. So I'm saving 70 iterations by using that break. Now, the difference between continue and break is that it might look similar by just replacing break and continue because I just did 30. But at the end of the day, if I moved the print here, and I'm going to put a line here, you're going to see, actually, let me swap it the way that we had it before. If I put a line here, you're going to see that there's 30 lines.
Lines. How come we didn't?
Oh, yeah. Once it got to 30, the first 30, let me just put it the first 30, just so that it's clear. The first 30, it's going to print a line. The last 30 is printing a number. Let me actually swap it because I was sorry. I apologize. Let me just swap that. we're gonna put, yeah, so we're gonna put the line for anything bigger than 30. So if it's bigger than 30, we are not executing this line below, but we're actually still counting. The counter is still going on. You see, like the first 30 items, it goes here. And the next 30 items is saying, oh, I don't need to execute this line. I'm just gonna use continue, which sends it back to this line. And then it's going in this loop where it's going back to here. Why is it useful, the continue? Let's assume that where was it? Thread. Ignore this. I'm just going to force that there's a 10 millisecond sleep for at the very beginning of things. Well, let's do 100 milliseconds because otherwise it's a little bit too slow. You see, it's a little slow, and then once it gets to the other part, it just avoids that sleep. And this is just representing a big amount of processing that we are skipping by using continue, because this part executes 100 times. This line executes 100 times when we are using continue.
So if we use break there instead of continue, then we would only do the first 30.
We would only do the first 30 and probably one time of the X.
Oh. Okay.
This line only executed 30 times because break exits the loop. The other one sends it back to the beginning of the loop. And it's like, no, well, I don't need to process anything below here, below the continue. That's continue. In the break, it's just like, I'm done. Let's exit.
And what would it look like if we just didn't have break or continue? Like this.
You see the slowness is still happening. Past 30, same thing. But it printed both things.
Oh, gotcha. So
This code continued to happen. That's why I'm putting like special emphasis on this part, because continue and break are important performance savers.
Okay.
Josh, did this help?
yeah, it's interesting that they choose to use the word continue, because it doesn't really mean continue where it was placed. It means continue the loop.
It is about continuing the loop.
Right. Yeah. But
Same thing with break, it's breaking the loop.
Well, break makes sense, but continue, it's not continuing. Yeah, it's continuing the loop, but it's also omitting.
Yeah, it's kind of like next.
Yeah.
So here's the thing, and this is something I want all of you to pay attention to. Whoever designed Java chose the worst keywords for a bunch of things, like static. At least if I read it without any context, I would understand what it's actually to be final, what the final keyword means, and we'll go through that. But there's a bunch of things in the language that I wish they would have been a little bit more careful with the choice of words, throwing the real things about Java. Okay, so everybody good on break and continue, right? All right, so let's talk a little bit about arrays, and then we're gonna go back to the other items. So arrays, let's go into our whiteboard, and this guy, we're gonna just delete this screenshot. Okay, so an array is an interesting data structure. It's the first data structure that C and C++ started with. And it carries the same traditions on Java. There are 3 conditions for an array. Actually, let me just explain how it is represented in memory. And this goes back to our earlier thing, but I'm just going to repeat it so that it's on video and you guys can actually go back and take a look. But this is our memory. Our memory has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines of RAM. Okay. And if we have an array, let's say 1, 2, 3, which an array basically is it's a list, but you're going to understand what's, for those of you that have done list or array in Python or JavaScript or something like that, this is a lot more primitive than that. So the way that arrays work is that when you declare an array, you have to specify the size first, and then later you can do the assignment, or you can actually do int x equals, and then you use the syntax to define it. When Java sees the syntax, it goes in and determines, oh, it's an, oh, sorry, I need the square brackets. Notice that the difference is that here the square brackets are empty, and here the square brackets have a number. When Java sees this, it's gonna read this and say, oh, there are 3 elements, therefore I know that it has a limit of 3. What Java immediately, as soon as it sees a line like this, it goes and says, I am going to reserve the memory for those 3 elements. And the memory for those has to be next to each other. That's how physically they are. Then once you execute this part of the code, then it puts 1, 2, and 3. So in an array, you have to have, first of all, because you're declaring it like this. When you do this, you're saying, I want to reserve an integer array of 3 elements. Or let me write it differently. 3 element or 3 integer array. And that might sound like, well, it's too obvious, you're reading it, but it has certain implications that are important to remember. Those implications are all the elements of the array have to have the same data type, all of them. Second, we have a known size, and the variable is it's an actual pointer to the beginning of the array. Now, because all the elements are next to each other in memory, we can jump from one element to any element of the array really quickly by providing an offset. So we can say array 2, it actually will mean the beginning of the array plus 2 jumps. Basically, array 2 starts here and then goes, and the actual value is 3. Again, this number, when you are referencing an array, beyond the declaration of the array, but when you are referencing it, you are saying the offset of that array. Therefore, array 0 would be what?
1.
Would be 1, because the value is wherever the array is pointing to plus the offset of 0, which yields 1. It's the beginning of the array. And that is something really important, because you will see a lot of times counters in any program or computer science starting at 0. So you'll see counters of 10 elements that start at 0 and then end at 9, because there's 10 elements there. but they start at 0 so that you can actually reference the first element of the array. But again, the array is referencing an offset. That's what it means, the offset from the beginning of the array. So when we are modifying a value, or when this is a write operation, and a read operation would be just essentially referencing the array, the element of the array that we want. Let's put it in code so that way it's a little clearer. Let's declare our array int array, and then we're going to say that it's a 10 element array, and we are going to set up a counter. Actually, I'm not even going to pardon me. I'm not even going to hard code here. Int array. Why is it not? Oh, sorry. This is the way to do it. This is the way to do it. You say, we're going to store an array, and it's going to be a new integer array of 10. This is how we're declaring it. I'm not even going to put the value of the array, because the array per se has an attribute, which is the length of the array. Just for informational purposes here, I'm going to write into the array into X, because that is going to hold a value of the current, X0, it's going to write to array 0. X1, it's going to write to the second element, and so on until the very end. And I'm just for this exercise, I am going to assign an X plus 2. Essentially, what I'm trying to do is I'm going to create an array like this: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 4, 5, 6, 7, 8, 9, 10. Yeah. So that's the array as we're going to do it. The offsets, actually, I am going to put 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Does this make sense? The offsets are in red. The actual values, are in black. That's basically what I'm trying to do. I'm going to populate an array that looks like this, even though that the offset values are like that. Everybody okay with this? Right now, I am going to then put a second loop for int X equals 0. We're going to start from the beginning of the array, while X is less than the length of the array, X plus plus, and then I'm going to print the values of the array. And we're going to get 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So we have this that matches. Again, this is, oh, I gotta remove this. This is a write operation. This is a read operation. And just to repeat myself, again, the 3 elements of an array is that it has to have same data type for all the elements. It has a fixed size, and it is controlled by an offset. Okay, so because it's a fixed size, what would happen the moment that we want to try to add a new array, a new element to the array? What do we need to do?
Increase the size.
Right, but we can't increase, like, we cannot just say, oh, okay, array, because if we did, we would reset the array.
Mhm.
So if we wanted to increase the size, we would have to create a new array,
Mhm.
copy all the values from the first, a new array with size +1, copy all the values from the previous one into it, and then destroy the old array. Which, that's the way that it works. That's the way that's the only way that an array can add a new element. We're going to learn about other data structures that go around that, because that seems terribly inefficient. Every time that you want to add a new element to the array, you're essentially duplicating the memory footprint. Does that make sense? So that's not very friendly, not very awesome, but that's the way that arrays work. And that was the first data structure that was built in. Okay, I'm gonna let you copy this for, where's my browser? Okay, here. I'm gonna set up a 3-minute timer, but before we do that, I'm gonna leave the code up here. Okay, let's copy that, just so that everybody is familiar with the syntax. Okay, let me answer the question from George. So a string would be, no, actually, if you want to pre-initialize an array, if you want to pre-initialize an array, and I'm going to put it down here, it would be like string fruits equals, like if you want to pre-initialize it, you use the curly brackets, and then you can put apple, orange, and berry. That's how you pre-initialize it. When you put the curly brackets, it is essentially knowing, oh, okay, I know that you're going to set up a certain set of values, 1, 2, 3, boom. It's an array of 3 elements. And it essentially what we did with these lines, actually, to put it like this, int array 2, essentially what we did with that is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's basically what we did with this. But I'm showing you two different ways of initializing that. Does that help, George?
Sure, yes, thank you.
Okay. All right. There's a couple of other concepts that I want to touch on. Earlier on, we talked about the pointers and this is something that was off video, but we talked about, I'm going to delete this reference. We talked about when we say, when we initialize the array, that we are actually pointing to the beginning of the array, right? And if we were going to say array 2 equals array, what ends up happening is that array 2 ends up pointing at the same area as array is pointing to. Therefore, if I say, let's change the value of array 2 to, 10, it would be changed in both. Now, we don't have to be like doing this loop for printing all the elements. Fortunately, Java has an arrays class that has all sorts of elements to like help us manipulate classes. So I can do like a toString, and I can actually wrap that around from system out.println, and then putting it as array toString, we're going to put the name of our array. And now if I run that, you're going to see, rather than printing it as a new line, it just prints it like this. So from this point on, I'm going to be printing arrays like that, unless I want to just specifically modify something. Let's make sure that, we declare int array 2 equals array. Once we duplicate that, and then we say, essentially, I'm going to be demonstrating what I just told you. Array 2 equals 10. We're going to print both array and array 2. And even though that I'm only modifying technically array 2 and not array, you're going to see that both get modified.
Wait, aren't you? Oh. Okay.
These gets modified and essentially because when an array is pointing to the same thing, it's essentially just copying a reference to the same memory location where both are located. Now, this might be a lot to absorb, and I understand, and we'll review a lot of it next class, and I'm sure glad that there's a video. But this is actually known as a shallow copy, meaning that when we performed this line here, this line, sorry, let me just re-highlight it. This line here, which is essentially this line, only the reference was copied. So it was a shallow copy. It was not a full copy. What would we need to do then if we wanted to copy the full array? Well, the better way, if we only wanted to modify array 2. So if we wanted to, we can do new int array dot length. So we're creating a completely new array. And then we do for int x equals 0, x less than array dot length. Actually, let's say array 2 because we're going to modify it. We're creating again our counter, and there we're going to say array 2 x equals array x. We're essentially copying value for value into that new array, so that when we modify array 2, array 2 is not going to be modified. Let's look at the results. You can see that array 2 was not modified, but array was modified in the second element here. That is because they are completely two different arrays. They're not referencing the same data. Essentially, what we did, assuming that we had more memory, what we did is that essentially what we did is we duplicated the array and did 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this essentially covers this thing, this slide. All these that we've talked about, it covers these two slides. Well, it also covers these because we talked about read operations, we talked about write operations, and we did a by hand exercise on sorting the following. We did talk about it a little bit earlier when we were doing the do while, where basically we're just comparing pairs of elements and determining if we need to swap them. So I'm going to try to do that in a second, actually, because the next thing that I just want to talk about is strings. We've talked about this briefly in the past, but strings is basically an array of characters. So we have a string and we have an array of characters saying H, E, L, L, O. We have an array of characters wrapped around an object where we are then throwing a bunch of different convenience functions for such object. We talked about this last class. If you want, Java provides the exception that, when you're using double quotes is a string. When you're providing single quotes is just a character. And immediately the moment that I put something like this into the compiler and I say string hello equals hello, it's going to say that that it's unclosed character literal. It's expecting a single character. The only way that I get rid of this error, well, is by naming it a character and actually putting it a single character. Again, even if I just did char hello and I wanted to do something like this, it's going to say that it's not a character literal because it's for a character literal to be a character, it needs to be only one character. For it to be a string, it needs to use double quotes, and then after that point, everything is valid. That's just the way that the language does it. And then from here on, like we did last class, then we can take advantage of all those methods that we can use. I feel like I don't need to spend much time in this because I've explained it in the past. But let's then think a little bit more in that two-dimensional thing. So we have string X. Let's say that, we were talking about from George, we have the fruit arrays, and we created our apple, orange, and berry. And when we have this array, there's an extra for loop that I skipped earlier on purpose, because there's this one that now that we've gone through this pain in the neck of iterating an array with the old school method, let's just, go and iterate with the fruit array like this. Let me just comment these guys out so that we know that we would have to essentially, and actually, like, we have to reference the arrays that way, and we have to, like, essentially type a lot more. Technically, what we're actually doing is something like this. Technically, that's what is happening. A new variable is being allocated of the reference, and that's what it's being printed. So there is another type of for loop that will allow us to dereference things without a counter. So we can do for string F on fruits. Oh, it's not plural. Let me just add another division item so that way you can see the before and after. It does the same thing, but these, let me add spaces here. You can see it does exactly the same thing, but these essentially dereferences, it goes for each F in fruit, similar to the iterator in Python. And then we can just print that directly. These two guys are essentially the same. This is more convenient because it gives you the variable directly to work with. Now, let me then get some numbers on strings and the for that format. Let me get some numbers on that. So then now that we have covered all those things, then I think it's fair to try to do the sorting algorithm. The super cheap, not efficient. Please don't hold it against me. This is not, there are 100 really efficient algorithms. This is the worst possible algorithm, but I just want to translate something that we've discussed into code and help you guys, this, going back to the cooking analogy, go from reading the kitchen book and navigating the kitchen to actually making a dish. So sorter, we're going to call our class the sorter class, and we're going to do something like this. And we're going to put, let's actually copy the same values that we had in this guy, the ages. We're going to sort these ages items. So we're gonna define int x equals 0, int x. Actually, yeah, so actually we can do something like, we're gonna do it with a do while because I promised you that it would be useful. And then we say has swapped. We're gonna do Boolean has swapped equals false. Technically, if I leave the out first, any default for any variable basically translates to 0. So 0 for a Boolean means off, and if it's off means false. 0 for a number essentially stays at 0. That means that the bytes are turned off. Then if we do 0 for an object, that means that it's null. So the default for anything that you don't initialize is 0, just as a quick reminder. So, but in this case, I'm just going to be explicit and say false. Oh, I moved it. So we're gonna do our loop while it has not swapped. And here what we're looking for is, have I swapped, yes or no? We're gonna start again the same. Every time that we do this, we're gonna set it up to false. Actually, technically, we could have done this, where every time that we are doing a repetition, we're gonna assume that we have not swapped anything. Then we're gonna say int x equals 0. And then we're gonna go through all the elements. So we're gonna do for int y equals 1. And why am I doing 1 in this case as opposed to 0? The reason is because, let me go back here, because if we have 24, 36, 14, 35, 22, 37, 42, and 25, if we have that array, we're going to be evaluating these two guys. So I want to make sure that this number of pairs, I keep essentially shifting it until it is safe. So I'm grabbing the first element, and this first element will be this last element once we make it to the end. If we grab this one and then we made it to the end, we might end up referencing the array plus 1 extra. So I'm going to start at 1 for now. So y less than ages dot length, y plus plus. Every iteration, basically, we're going to start with x equals 0 and y equals 1. This is going to be x. This is going to be y. This x and y. That's how we're going to start everything on the array. Now, I hope that this makes it a little bit clearer why I'm choosing 1. Does that work? Yeah. I only saw George nod.
Yeah. Explain it one more time.
Okay. So if I am starting at, I need to establish a mechanism that I don't go overboard, that I don't go past the array, because otherwise I'm going to be referencing memory that doesn't exist. And we have determined that we're going to be comparing pairs.
Mm-hmm.
So if I'm starting with x as 0, I already have x covered outside. I need to start with y as 1, so that y starts from 1 all the way till the end. So by the time that y equals this guy, x will be this guy. So then we'll be comparing, the pairs all the way.
Okay.
So we have a full coverage of pairs. Okay, so this x equals 0 and y equals 1 is essentially the starting condition that we have here. Okay, so then we're gonna do an if ages X is greater than ages Y. Actually, let's rename X and Y. Why don't we just say, so go for like first, and then we do second. Just so it's a little bit, even a little bit more under, we know, we're evaluating the first number and we're evaluating the second number. I hope this makes it a little bit clearer for everyone by renaming the variables. Okay, everybody following me? Yeah?
Yep.
Okay, want to make sure, is anybody behind? No? Okay, so we know that if the first is greater than the second, given what we had talked about in the past, we would swap. So then we're going to create a temporary variable where we're going to store either the first or the second, doesn't matter. In this case, I'm going to store the second. Then ages second, I'm going to put the first. And then ages first equals the temporary value. That's how we're swapping the value. Why? Because if I go ahead and let's assume that I got to delete these two guys. And if I say, oh, okay, I'm going to swap them. I'm going to delete this guy here. Oh, no, I was doing second. So I'm going to do the second. Okay, I'm going to delete this guy here. And then I'm going to put 24. And then I'm going to delete this guy here. And what was the value that I had before? So that's why before doing the swap, I am saying we're going to put it in a temporary value, this 36. Now I can go ahead and delete it, copy it with 24. And now this guy, I can put it back in 36. Well, that is assuming that I had to swap, but in this case, it was not necessary because this is not bigger, but these two are. Does that make sense, or did I confuse anybody? And because I swapped, because we know that if it went here, I did swap, so I gotta change this to true. And then at the very end of it, because it's going to continue doing it until it doesn't have to do any more work, we can do a print of our arrays to string ages. And you're going to see that our array is now sorted. Oh, no, it didn't sort. Hang on. So this is where debugging actually works. So let me put it right here. Let's debug it. And we are in this situation where we want to oh, I know why. Okay, so as we're iterating, every single time that we're incrementing this, we also have to increment first, because otherwise what was happening was that we kept this guy static. We were comparing, we were doing this comparison. This and this. And if we are not, and the for loop is essentially doing this, and then it keeps moving the pointer on each iteration, and then moving it here, but the red is staying the same. So what I gotta do is to increase every time that we are increasing this, we gotta increase the other one. So that way, when we start like this, then the next iteration, we do this. And then the next iteration, we do this. and so on. So both pointers are moving concurrently at the same time. So now if we ran it, in theory, it is sorted now. Any questions about this? Let's get some numbers about this algorithm. Okay, sounds good. All right. So then let's do like just the 3 minutes to copy this and oh no. Where did it go? Where did it go? Here. Here. Let's do the timer. Let's copy these, and then we'll go through any one-on-ones and stuff.
So if we don't do this with a do while, do we just use 2 for loops?
Yeah, you could use 2 for loops, yes. The only reason why I'm putting the do while is because at the very least you got to check that the arrays is done one, but you technically could do it with the other one. Yeah. Okay. Any last minute questions then, so that I can then go into one-on-ones with whoever needs them? No? Okay. So then for tonight, then class dismissed.